Hi everyone, I am Santhi from Department of Mathematics and Statistics, Bhavan's Vivekananda College. I am here with my lesson 12 from linear algebra on vector spaces. In this lesson, I am going to explain about basis of a vector space and its subspace. So first let us see what is basis of a vector space. Before I define the basis, let us recollect. If you take a vector space V, you can find many sets of vectors like set B, which is B1, B2, B3, and so on, BP in vector space V. Like that, so many subsets will be there in a vector space V. Among all those, some will be linearly independent sets, some will be linearly dependent sets, and some sets will be spanning the entire vector space, which we call them as linear spans. So like that you have different sets in a given vector space. Then what is a basis? So let us see the definition. Let V be a vector space. An indexed set of vectors B is equal to set containing B1, B2 and B3 and so on BP, some P number of vectors in the vector space V is said to be a basis of V if number 1, the first point, B is linearly independent. This set of vectors B must be linearly independent. And the second condition is the vector space V is equal to span of these vectors, whatever the vectors given in B. Span of B1, B2 or B3 and so on BP. What do you mean by this? Each vector in the vector space V can be expressed as a linear combination of B1, B2, B3 and so on BP. That is the vectors in B. Then we say V is spanned by the set B. So the set B must be linearly independent and it must be spanning entire vector space V. Then we say that set B as a basis of a vector space. After the definition, let us see the standard ordered basis for R2, R3, R4 and so on Rn. Before starting this, we have these basic vector spaces which we have been going through from the beginning of the vector spaces topic. So we know what is R2. Now let us take this R2, and in this R2 let us consider set of unit vectors. This we have seen earlier, 1, 0, 0, 1 are unit vectors in R2. So you call E1 is 1, 0, E2 is 0, 1. Then we already earlier we proved when we were discussing about linearly independent sets, this set of unit vectors in R2 is linearly independent. Now let us see, can it form a basis for R2 or not? To form a basis, what are the two things it must have? It must be Li, and the next one is the vectors in this must span R2. So let us see. Let me take a vector u in R2. How will it be u in R2? In R2 you will have a column vectors of 2 rows. So I've taken a general vector AB. It can be any vector in R2. So now let us try to write it as a linear combination. So 1, 0 and 0, 1. That is, you can write u is equal to AB as A into 1, 0 plus B into 0, 1. What do you mean by that? Any vector AB you take in R2, you can write it as a linear combination of these two unit vectors. That is AB is equal to A times 1, 0 plus B times 0, 1. What do you mean by that? The entire vector space R2 is spanned by these two vectors. That's what we meant by span. Any vector in R2 can be written as a linear combination of these two. Now, whatever the set we have taken, set of unit vectors, is linearly independent and it is also spanning R2. Then we can say that it is a basis for R2, and we call this set of basis of unit vectors for R2 as standard ordered basis of R2. This order is important. First element is 1, 0, second element is 0, 1. That's why we call it as standard ordered basis of R2. Similarly, if you take R3, what are unit vectors in R3? 1, 0, 0, 0, 1, 0, 0, 0, 1. So the set of unit vectors in R3 forms standard basis of R3. The same way you can have a standard basis for R4 and so on. The set of unit vectors, even E2 and so on En. How many unit vectors will be there in Rn? N number of unit vectors. You can check here. In R2, 2 unit vectors. In R3, 3 unit vectors. So in R4 you will have 4 unit vectors. And in Rn you will have n unit vectors. These form standard basis of Rn. So now I gave standard basis of R2. Now is this basis unique? We'll discuss a theorem and all later, but here I can say this note point is a vector space can have more than one basis. It's not unique. Here we mentioned that in R2, what is the standard basis we have taken? Unit vectors, set of unit vectors 1001 is the standard basis. But suppose I considered another set 1 to 2, 5. So this also forms a basis of R2. How it is we can check in the next coming examples. You will understand how will the other sets other than sets of unit vectors form basis. So what do we understand by this is these vector spaces have standard basis with unit vectors. Apart from that, these vector spaces can have any other basis also. Infinite number of bases it can have. It's not that basis is unique. The same way, let us look at the standard ordered basis for the vector spaces P1, P2, P3 and so on Pn. We know what are these P1, P2, P3 and so on Pn. They are vector spaces of polynomials. So let us see for this first one P1. So in P1 we can take this set 1 comma t. With this earlier we discussed that this set containing 1 comma t will form Li set in this. Now what is P1? The vector space of all polynomials of maximum degree 1. Now let me take this set is Li because this we proved earlier that it is Li when we were discussing about linearly independent sets. Now let us see whether this set can span all the vectors in P1. So I'll take a vector in P1. What are the vectors in P1? All polynomials of maximum degree 1. So let me take a general polynomial, that is linear polynomial a plus bt. T is a variable, a is a constant and b is also a constant which is coefficient of t. So I have taken a general vector linear polynomial in P1, that is a plus bt. Now I can write it as a linear combination of 1 comma t. How? U is equal to a plus bt. I can write it as a into 1 plus b into t. So with the scalars a and b, I can write it as a linear combination of 1 and 2. What do you mean by that? Any vector you take in P1, it can be written as a linear combination of 1 and t. It means the entire vector space P1 is equal to span of 1 comma t. It is spanned by these two vectors. So we can say this set containing 1 comma t in P1 forms standard base ordered basis of P1. Standard and order is important. First vector is 1, second vector is t in P1. Similarly, if you take P2, what is P2? The vector space of all polynomials of maximum degree 2. So what is that basic set? In that you will have 1t t square, first constant, first degree term, second degree term. Then 1t t square set if you take, it forms standard basis of P2. And in the same way for P3 you can have standard basis, ordered basis, that is 1t t square t cube. Then if I take Pn, the vector space of all polynomials of maximum degree n, then what is the set? 1t t square and so on t power n forms standard ordered basis of Pn. As we discussed earlier for R2, R3 and so on, a basis is not unique. For P1, if this is one basis, which is standard ordered basis, it can have many other bases also. Similarly, P2 also can have any other basis and so on. Any vector space can have more than one basis. Now let us see how to check a given set of vectors B forms a basis for a given vector space. So according to definition, we have to show that set B of vectors in a vector space is linearly independent, and another one is it spans the entire vector space. So following that, so the first point what you have to do is find whether B, the set B is Li. So for this, what method you will follow? You will use echelon form. So earlier classes you have learned how to check a given set of vectors is linearly independent or not using the echelon forms of matrix. The same way you will do this. Then what is the second one you have to check is, then find whether the vector space V is equal to span of, it is spanned by the set B. This is what you have to check. For this, what you do is you will use, so the procedure for this is, for this you will consider a matrix, consider a matrix A, a matrix A with the vectors in B, with the vectors in the given set B as columns. B as columns. The set is B as columns. That is what will be our A. A is equal to, suppose you have B1 is the first column in B and B2 is the second column in B, and so on. BP is the last column in B. Then you will use this reduce A to echelon form, reduce A to echelon form, and so these are the points you have to do. If each row in echelon form, if each row in echelon form, it is understood each row has a pivot position. If each row in echelon form has a pivot position, then the set B spans V. So what is the condition? You have to first reduce A to echelon form, and if each row has a pivot position, then B spans V. This is what you have to do when you have to check whether a given set of vectors can form a basis or not. Suppose the first condition B, when you find it is not Li, then you don't need to check the second condition. And sometimes P may be Li, but the second condition may not be satisfied. When both the conditions are satisfied, then only that set B forms a basis for the vector space. Now let us see one example how to check whether a given set of vectors forms a basis. So here you are given three vectors in R3 and you have to check whether they form a basis or not. Let us see the solution. So here let me take the vectors as V1 is equal to the three vectors, let me call them V1, V2, V3. Okay, so now what is the first condition I have to check here? First one I have to check whether they are Li or not. That is whether set containing V1, V2, V3 is linearly independent or not. This is what you have to check in the first one. So for this, how do we do checking for linearly independent? So I'll consider A1 V1 plus A2 V2 plus A3 V3 is equal to 0. And that means using all this you will get, and we know this will give us A1 into 1 0 minus 3 plus A2 into 3 1 minus 4 and plus A3 into minus 2 1 1 is equal to is converting them to equations, and after converting them to equations we will get these equations, that is A1 plus 3A2 minus 2A3 is equal to 0, and then A1 into 0 0, then A2 plus A3 is equal to 0, and the third equation is minus 3A1 minus 4A2 plus A3 is equal to 0. And this system we will solve, and how to solve this using the echelon form we know. So we will consider the matrix. So augmented matrix. Augmented matrix. So what is that augmented matrix is for me here? So that it is nothing but again the same vectors we know after writing the equations also. If you take these coefficients 1 3 minus 2, but still you will get the same vectors here 3 1 minus 4 and whatever you are given here. So directly also you can write this is the augmented matrix. So next we'll have this augmented matrix we have to. So whatever the vectors given to us, these are the vectors given to us, we have written them as the equations. Then these equations we are using the echelon form augmented matrix, and then the echelon form we will do it. So for this, how do we reduce this to echelon form? So what are the operations we are going to apply here? So this is the pivot position. So you have to, this is already 0, you need not change anything, only that you have to do it for R3. So R3, I will just R3 plus 3 times R1. So you have been doing this, all this in the previous problem. So straight away, so let us write the values. So this is 0 1 1 0, and then this is 0, and then minus 4 plus 3 into 3 3 3 is 9. So you will get here, then this is 0 5, and the next one is 1 minus 6 is minus 5, and then 0. You have the next step. What we have to do here? This pivot position is over, and this is a pivot position, and here you can observe this R3 can be simplified more. So just divide R3 with 5. So this is reduced to 1 3 minus 2, and then 0 1 1 0, and this is 0 1 minus 1 0. Again mark the pivot positions. So the next one here you have is this we have to R3, you have to make this one 0. So we will do for R3 minus R2. So this will be 1 3 minus 2, and then 0 1 1 0 and 0 1 minus 1 0 minus 1 minus 1 is minus 2 0. Now this echelon form is completed. You have 3 columns. All the 3 columns are pivot columns. So 3 pivot column. Therefore, what are the basic variables? All 3 variables are basic variables, that is A1, A2, A3. No free variable. When there is no free variable, what do we conclude here? It is the solution will be only unique solution, that means zero solution, which implies linearly independent. Now we'll go for the second condition. So what do we do in the second condition? In the second condition, we have to consider the given vectors, whatever the vectors are given here, that we have to consider, and you have to check here whether the given R3 is a span of V1, V2, V3, the given vectors. For this, what is the method we explained here? Take a matrix A is equal to the columns of the columns, these vectors as columns, that is 1 0 minus 3 and 3 1 minus 4 and minus 2 1 1, and reduce it to echelon form. See, this reducing this to echelon form or previous augmented matrix, what you have, both are the same, operations are the same, only here you have one column extra 0 zeros, otherwise the operations are the same. So I can write here the transformations. This is pivot positions, so I will use the same transformations. Then R3, so 3R3 plus 3R1, so this will give me 1 3 minus 2 and then 0 1 1 minus 3 minus 4 1, the same steps we are repeating. So this is sorry, this one will be after the these will become 0, and next one it will be 5 and then minus 5. Now using this again, we have divided R3 as R3 by 5, the same steps. So this is transformed to 1 3 minus 2 0 1 1 and 0 1 minus 1, and then again we have done R3 for R3 minus R2. So this is transformed to 1 3 minus 2 0 1 1 0 0 minus 2. Now what do you have to check here? R1 there is a pivot position, R2 there is a pivot position, R3 there is a pivot position. So what do you write here? Each row has a pivot position. Then what will be your conclusion if each row has a pivot position? Implies R3 is spanned by these given 3 vectors. So this is V2, V3. That implies, so what can you say implies by 1 and 2, the given vectors set containing V1, V2, V3 forms a basis for R3. Look at this problem. Determine whether the following sets of vectors, first bit is Li, second bit is span R3, and the third bit is Li and span R3 both. So here we are given with the 2 bits. Let us see the first one, first problem. Let us take the A bit. So in this the first question. So what are the vectors given in the first one? 3 minus 3 0, and then minus 3 7 0, and the third vector is 0 0 0 and 0 minus 3 5. Right. Now let us do the a bit. What is a bit, whether they are li or not. But here, since there is a 0 vector, they cannot form, they cannot be li. So with this we have written earlier when we were talking about linearly independent, linearly dependent sets. Then we can write they cannot be linearly independent. So first bit we have completed. Now let us do the second one, whether they span R3 or not. So for that, what do we have to take? We have to take a matrix. In this we will take these columns as elements, and 0 minus 3 5, and we have to reduce to echelon form. So this is here pivot position, so only this R2 I have to change. So for R2 we will apply R2 plus R1. So this will be reduced to 3 minus 3 0 0, and then 0 7 minus 3 4, 0 minus 3, and the last one no need to change anything. Now let us mark the pivot positions. This is pivot, in the second row this is pivot, third row this is pivot. So it is reduced to echelon form. Now what do we have to check here? R1, in R1, yes, there is a pivot position. In R2 there is a pivot position. In R3 also there is a pivot position. So what do we write? R1, R2, R3, all three have pivot positions. Therefore, they span R3. So though they are not linearly independent, they span R3. So what is our B bit answer now? From A and B, they cannot form basis of R3 because they are not linearly independent. What are the vectors we have in the second bit? Second question, or let me see the second one. You are given with the two vectors, minus 2 3 0, and then 6 minus 1 5. So for this let us see a bit, that is Li or Ld. So how do you do Li or Ld? Directly I am taking the augmented matrix, that is minus 2 3 0, 6 minus 1 5, and 0 0 0. So where is the pivot position here? So using this you have to make the second row 0. So for R2, what do I apply? 2 times R2 plus R1. So 2 into 3 6, not plus R1, plus 3 times R1. So this will give me minus 2 6 0. So 2 3 6, minus 3 2 6 0. 2 into minus 1 minus 2 plus 18. Minus 2 plus 18 is 16. And then this is anyway 0 only, and that I am not changing anything here. Now mark the pivot positions again. This is pivot position. And the third row, do you have any pivot position? No, but still you have to try to make this one 0, no? So let us see. For R3, we will divide R3 by 5 first. So I will get here the matrix minus 2, 0, 0, and then this is 6, 0, and 16, 0, 1, 0. Now again mark the pivot positions. Now you have to make this one as 0. So for R3, what do you do? 16 times R3 minus R2. So this is transformed to minus 2, 6, 0, and then 0, 16, 0, 0, 0, 0. Though you have done again transformations, you cannot fetch any other pivot position in this. So here you have how many columns you have for this LI. What do you do? We'll take this as C1 and C2. How many columns? 2 columns. C1, C2 are pivot columns. Implies whatever the variables we have taken, A1, A2 we have not taken, or basic variables. Is there any free variable? No free variable. If there is no free variable, what do you say about that? You will say that they are linearly independent. There are only 2 vectors in R3, but still they are linearly independent. Now we have to see whether they form linear span or not. So how do we check for the linear span? That is our B bit here. That is linear span. So for a linear span, what do? You will take A is equal to matrix which contains these minus 2, 3, 0, and then 6, minus 1, 5. Only these. And you will apply the same operations. So if you apply the same operations, what happens? For R2, 2R2 plus 3R1. So this will give you minus 2, 6, 0. And then what did you get here? 2 times minus 2 plus 18 is 16. And then 0 and 5. So this one and this. And the next what you do is we will apply for R3 by 5. The same operations what you used in LI, the same operations you will do here. So you need not repeat. Sometimes you can just write as in the previous. So this is again this is pivot, and then this is pivot, and then you will do R3 for R3 16 times R3 minus R2. So this will give you minus 2, 6, 0, 16, 0, 0. Now what do you do for the linear span? You will check in R, this is pivot position. In row 1 you have pivot position. In row 2 also you have pivot position. But in row 3 you don't have a pivot position. Then what do you mean by, what do you write here? R3 does not have a pivot position. Therefore, they cannot span, they do not span the vector space R3. So now what is your C bit answer? Since though it is Li, it is not spanning, hence they do not form basis. So now what do you observe in these 2 bits? In the first bit, you are given 4 vectors in R3. Since 4 vector in R3, and also one more thing, there is a 0 vector, they cannot be Li. That means in R3, one thing is more than 3 vectors cannot be linearly independent. This we discussed earlier. At the same time, since there is a 0 vector, they cannot be aligned. And what about the second one? There are less than 3 vectors, 2 vectors in R3, but they are Li, but they cannot span. That means R3 cannot be spanned by less than 3 number of vectors. It can be spanned by more than 3 number of vectors, but it cannot be spanned by less than 3 number of vectors. Now, after working out a few problems on basis, where we were given a set of vectors and you were checking the two conditions, whether that set is Li or not, whether that set is spanning the given vector space or not. If both conditions are satisfied, it is a basis. If any one condition, you have seen some examples where some sets are satisfying Li condition, they are not satisfying the span condition. Then some sets are satisfying the second one and they are not satisfying the first one. So by observing all these, we can jot down some points, important points to remember here. So the first point, this is here I have given Li, this is for linear span. In Rn, a set of more than n vectors cannot be Li. What do you mean by this? Suppose I take R2. In R2, if I take 3 vectors, 4 vectors, 5 vectors, they cannot be Li. That means in R2, a set of 2 vectors or 1 vector can be Li, but more than 2 vectors if you take in R2, they will always be LD, they cannot be Li. You need not check, you need not work out this point we discussed earlier also. Then span, what about span? In Rn, a set of more than n vectors may or may not span Rn. Now in R2, if you take a set of more than 2 means 3 vectors, 4 vectors, 5 vectors, they may span, they may not span, but they cannot be Li. Now let us see the second point. In Rn, a set of less than n vectors, then they may or may not be Li. This is just opposite to the previous point. That means suppose if I take in R4, a set of 3 vectors or 2 vectors or 1 vector that may be Li or may not be Li. But here if you come for linear span, in Rn a set of less than n vectors cannot span Rn. That means if you take R4, if you take any number of vectors 3 or 2 or 1, they can never span Rn or R4. Only 4 vectors, set of 4 vectors or more can span, but not a set of less than 4 vectors span R4, right? Now let us see the third point. In Rn, if a set of exactly n vectors is Li, then it forms a basis. So this point is making our finding a basis like checking whether it is a basis or not. It's a simple. That is, in Rn, if I have a set with exact n vectors, if I check Li, that's enough. I don't need to check span. It automatically spans Rn, no need to check. For example, in R5, you take a set with 5 vectors, then just show that it is Li, enough. Then you need not check for the span. Right? Now on the other hand, if I come for linear span, in Rn, a span of n vectors is there, then that forms a basis. That means the same way in R5, you take 5 vector set. If that set is spanning R5, then it forms a basis. You need not check for Li, it automatically forms a basis. So we can just generalize this third point. In Rn, if you are given set of exactly n vectors, either you check Li or you check span, you need not check both. Suppose in R6, you are given 6 number of vectors exactly. If you want to check it for basis, just check either Li or span, any one. You don't need to check the other one. It will automatically be satisfied. Hope this makes our checking whether a given set is a basis or not more easier. Now keeping the previous points we discussed in view, let us check at these three problems whether they form basis or not. The first one, here I have 1, 2, 3, 4 vectors. We have 4 vectors in R3. What do you mean by that? That is, you have 4 which is greater than 3, that is more than 3 vectors in R3 implies they cannot be Li. More than n vectors in Rn, they cannot be linearly independent. So therefore, I can write here, they do not form basis for R3. Right. Now let us look at the second one. How many vectors you have? I have 2 vectors in which vector space? In R4. So that is, you have 2 which is less than 4. Then what is that point we had? Less than 4 vectors in R4 which cannot span, less than n vectors in R4 which cannot span R4. Then can they form basis? No. Therefore, they do not form basis of R4. Now let us look at the last one. How many vectors I have? 1, 2, 3, 4, 5 vectors. 5 vectors in R5. So that is, you have 5 is equal to 5. Exactly 5 vectors in R5. Then how can, whether they form a basis or not, and what do you have to do then? Check either Li or linear span. Any one is enough. So you check either they are Li or either they are they form linear span. No need to check both, because when this one number of vectors is equal to, here this R5, 5 is equal to 5, then you can check any one of these two. No need to check for the both. Now, basis of a subspace. Before defining what is a subspace? A subspace is also a vector space on its own. So a basis of a subspace will be same as basis for a vector space. So its definition will be like this. Let H be a subspace of a vector space V. An indexed set of vectors B is equal to set containing B1, B2, B3 and so on Bp. In H, it is said to be a basis of H if B is linearly independent and H is equal to span of the vectors in B. That is, each vector in H can be expressed as a linear combination of B1, B2, B3 and so on Bp. It is just same as a basis for a vector space.